All right, so number one here, we're looking at the limit as x approaches -1 from the left. And if I just plug in -1, I get a 0 on the bottom, which means we have a discontinuity right here at -1. The problem is there's nothing that I can do to get rid of that discontinuity. So it's non-removable because there's no way we can get rid of this x on the bottom. We can't factor. There's no conjugates. So we know that this is a non-removable discontinuity. And I'm only looking at what's happening to the left. So you're welcome to plug that in. Something just to the left. Now we're looking really close to -1, but to the left of -1. So if you plug in maybe -1.001, we know that because this is non-removable, it's probably going to infinity. Whatever it's going to, whether it's infinity or negative infinity, as this top gets bigger than the bottom, either way, we know that the limit does not exist. Okay. Number 6, if we're looking at the limit as x approaches 1 of x minus 1 over the absolute value of x minus 1. Now, we want to be careful with the absolute values. Obviously, if I plug in 1, I get 0. So we know that there's a discontinuity here, but we want to see what is happening. And remember, with absolute value, what that could mean is that whatever's getting plugged in on the inside could be a positive or a negative. You're going to get the same result. So when I rewrite this limit, I actually have to look at x minus 1 over not just x minus 1, but I have to look at the positive and the negative x minus 1. So if I'm looking at the positive, I've got x minus 1 over x minus 1, which is just 1 over 1. If I look at the negative, I get x minus 1 over the negative x minus 1. And when these cancel, I'm left with 1 over a -1. So I get -1. So my limit, I'm getting two different answers. I'm getting 1 and I'm getting -1. So we know that this limit also does not exist. Okay, now looking as x approaches -2, again, if I plug in the -2, I get x -2 cubed, which is -8 plus 8 is going to give me 0. So I've got a discontinuity there on the bottom. And this one requires you to remember a formula that we talked about. We talked about the sum and the difference of cubes. And remember, if it's on this practice test, it's going to show up on the test. So it's going to be a good formula, something that you need to know. So if you remember, the sum of cubes says that a cubed plus b cubed is equal to a plus b, if I remember the b, multiplied by a squared. And if this is a plus, then in between we've got a minus ab, and then we have a plus b squared. If it's a cubed minus b cubed, remember that one is a plus b, or excuse me, a minus b, and we get a squared plus ab plus b squared. Okay, so remember that middle term is going to be the opposite of whatever we have over here. So using those formulas, we can factor this on the bottom. We can rewrite it so that we still have our x plus 2 on the top. But if you can recognize that 8 is actually 2 to the third power, this becomes x cubed plus 2 cubed. So I'm going to use this formula right up here to factor out the bottom, and that's going to become x plus 2 multiplied by x squared minus 2x. And then when I plug in 2 to the 2 squared, that becomes plus 4. So my x plus 2's cancel, and I'm left with 1 over x squared minus 2x plus 4. So now when I plug in -2, I can try to do direct substitution again. When I plug in the -2, I get 1 over -2 squared minus 2 times -2 plus 4, which is just 4 plus 4 plus 4, which becomes 1 over 12. So my limit as x approaches -2 is going to be 1/12. Now you can check this on the calculator if you want to plug this in. If you want to go to the graph, remember you go to y equals, and I'm going to put x plus 2 on top. Actually, let's go ahead and make a fraction first of all. And on top, we're going to put x plus 2. And on the bottom, we're going to put x cubed plus 8. So if I do x cubed plus 8 on the bottom, whoops, make sure you drop out of there, plus 8. And when I graph that, what we're looking at is at -2, I should be getting close to 1/12. And if you were to zoom in on this, when I'm getting to -2, it looks like I'm really close to 0, and 1/12 is actually really close to 0. So we're probably in the right spot. But if I wanted to be sure, I could look at my table. And remember, I can't plug in -2. If I plug in -2, that was our discontinuity. So I get an error. But if I plug in, since we're looking at the limit, if I plug in -1.999, I get 0.8338. And if I plug in -2.001, I get positive 0.08329. So I just want to make sure that that's close to my 1/12. So if I do 1 divided by 12, I get 0.083, which is really close to where we were at. So I'm confident that this here is going to be the correct answer. Okay. All right, number 7. I know I'm kind of jumping back and forth left and right. Hopefully you can follow along okay that way. As x approaches 0, again, the bottom is going to go to 0. This time, we want to multiply by the conjugate to get rid of this on top, to kind of try and simplify and maybe factor or cancel something out. So that square root's your hint that you're going to use the conjugate. So on top, I'm going to multiply by the root of x plus 9 plus 3, which means I have to multiply by the same thing on the bottom, root of x plus 9 plus 3. Now remember, when you're multiplying by a conjugate, your middle terms cancel out. So all you really need to worry about is when you multiply the first 2 terms and the last 2 terms. So I'm going to end up with the square root of x plus 9 times the root of x plus 9 is just x plus 9. And -3 times 3 is -9. And those are going to cancel on top. So all I'm left with is an x on top. We're off to a good start here. And then on the bottom, I have x multiplied by root x plus 9 plus 3. So now my x's are going to cancel top and bottom. And all I'm left with, remember, what's left over is on the bottom. So I need to be careful to put the 1 on top. And I've got root x plus 9 plus 3. So now when I plug in 0, I get root 0 plus 9, which is just the root of 9, which is 3 plus 3 on the bottom. Remember, I've got 1 on top, so that becomes 1/6. So it looks like I'm approaching 1/6. And again, if you want to plug that into your calculator and look at the graph, it's going to look like you're getting really close to 0. And you can check on the table when you plug in something bigger or smaller than 0 and make sure that you're getting close to 1/6. But I'll let you do that on your own. So let's jump over here to number 3. I'm looking for the limit as x approaches 0. Now, when I plug in 0 right here with the 3x, that's okay. I can do 3 times 0. Nothing wrong with that. But when I plug it in over here, I get 0 squared, and I have 0 in the denominator, and that's not okay. And unfortunately, I don't see any way of canceling out this x squared. If this was an equation, I could multiply everything by x squared, but it's not. We're looking for our limit. So that x squared, there's really no way to cancel that x squared on the bottom. So I know that it's non-removable because I can't get rid of that 0 on the bottom. And it looks like it's probably, if I were to graph this, it looks like it's probably going to go to infinity. But wherever it goes, whether it's infinity or negative infinity, I know that that limit does not exist at that point. Because if we wanted to look at specifics, you could plug in these values and plug them in, a value to the left of 0, a value to the right of 0. And what you're going to get right here is 1 on top, and on the bottom, you're going to have something like 0.0001 squared, which is a really small number, which tells me that this is going to infinity. And that's going to leave me with a limit that doesn't exist. Whatever it is, we know it doesn't exist. Okay. Let's go down to number 4. X squared minus 4x plus 4 over x squared minus 6x plus 8. Now this time I'm only looking at what's happening to the left of 4. So I'm looking at what's happening as I approach 4 from the left-hand side. And seeing all these quadratics, I'm assuming that I'm probably going to be able to factor and maybe cancel something out. So if I start with the top, x squared minus 4x plus 4, I'm looking for something that multiplies to 4 and adds up to negative 4. If you guys did you had McConnell, so you probably did your x factoring. So I'm looking at what adds up to negative 4 but multiplies to 4, and you get your negative 2 and negative 2. Now I'm going to actually write x minus 2, x minus 2. I'm not going to put the squared because I'm hoping that there's an x minus 2 on the bottom that will cancel. So when I look at the bottom here, I'm looking at what adds up to negative 6 and multiplies to 8. So if you do your x factor again, you will see that negative 2 and negative 4 multiply to 8 add up to negative 6. So I get an x minus 2 on the bottom and an x minus 4 on the bottom. So luckily I got x minus 2 on both. So those cancel, and I'm left with x minus 2 on top and x minus 4 on the bottom. Now when I plug in 4, I still get 0 on the bottom. So I wasn't able to make that 0 go away. And at this point, there's nothing else that I can do to simplify or get rid of this x on the bottom that's going to make it go to 0. So since it's still 0, we know that there's an asymptote at that point, and our limit is not going to exist. So the limit does not exist as we're approaching 4 from the left. And you're welcome to, if you go ahead and graph that function, what you'll see is as you're approaching 4 from the left, and let's go ahead and do that really quick. Let's get rid of this one here, and let's graph. The nice thing about the videos is you can always fast forward if you don't want to watch the graphing. So I'm going to do x squared minus 4x plus 4 on top. And then on the bottom, whoa, clearly I'm not looking at my screen. Let's try this again. X squared minus 4x plus 4. And then on the bottom, I'm getting x squared minus 6x plus 8. And what I'm hoping to see is as I approach 4, I'm going to hit an asymptote. So as I'm coming from the left, I'm getting closer and closer to 4, and there it is. Clearly there's an asymptote there at 4. At least it looks like there is, so we can assume that we're working in the right direction there. Okay. Let's go ahead and do number 5, and then we'll jump over to these piecewise functions. So number 5, hopefully you recognize as one of those special rules that we talked about when we're dealing with trig and limits. So this is one of those special rules, and it looks the rule itself doesn't look exactly like this. What we told you before, that at the limit as x approaches 0 of sine x over x is equal to 1. Well, in this case, I'm not approaching 0, I'm approaching 2. But what happens when I do this limit is it ends up looking like the sine of 0 over 0. And I know that the sine of 0 over 0, as I approach that limit, I go to 1. Well, look at what happens when I plug a 2 into this function. I end up with the sine of 2 minus 2, which is 0, over 2 minus 2, which is 0. So even though my limit's not approaching 0, this is just a horizontal shift of the function. And so my limit is still going to be 1. Again, that's one of those special rules that you're going to need to memorize. And like I mentioned before, it's on the pretest. So it would be a good idea to be comfortable with that one for the actual test itself. So let's look at these piecewise ones. As limit as x approaches 1 of f of x. Now, with our piecewise functions, we've got to remember that we're not interested in exactly what happens at x equals 1. We are looking at what happens near 1. So what I see a lot of students do is they do direct substitution. They say, oh, well, when x equals 1, then my value is 2, so the answer must be 2. But remember, we're not interested in what happens at 1. We're interested at what happens near 1. And in that case, when I'm near 1, I'm not at 1. So I've got to use my top function. I've got to use the x squared plus 4. So I can't just direct substitute the 1 in the bottom. I have to plug it in the top. So when I plug in a 1, I get 1 squared plus 4, which is 5. So my limit as I'm approaching 1 of this piecewise function is 5. Even though at 1, I have my point is 2, my limit is still 5 because it's what's happening near 1, not right at that point. So same idea here with number 9. As x approaches -3, now I have 2 different piecewise functions here. Or I've got one piecewise function, I've got 2 different scenarios. When x equals -3, I get -2. Well, I don't care about when x equals -3. I want to know what happens when x is near -3. So I'm going to plug in -3 to this function. And as I get near -3, I'm approaching 5, even though once I actually get to -3, I'm getting to -2. That's funny. We ended up with 5 on both of those. So your limit's going to be 5. Now we've got to be careful when instead of equals and not equals in our piecewise functions, when we're dealing with a less than or greater than. So for example, number 10 right here says that if x is between 0 and 3, then I'm going to use this function on top. If x is between 3 and 6, then I'm going to use this one on the bottom. Now, in this case, I can't just plug in as I approach 3. What's my limit as x approaches 3? I can't just plug it into either one of these because I want to know what happens to the left and to the right. And so when I look at these, one of these tells me that as I'm approaching 3 from the left, as I'm going from 0 to 3, this is my function that I need to use. And as I approach 3 from the right, so as I'm going from 3 to 6, this is when I'm approaching from the right, then I need to use the function on the bottom. Okay, so if I go ahead and let's plug in 3 to both of these. If I plug it into the top, because we want to see what's happening to the left and the right. So 4 ln of 3 squared becomes 4 ln the natural log of 9. If I plug it in the bottom, I get 8 times 3 over 3 natural log of 3, which becomes the 3's cancel, so I just get 8 natural log of 3. Now, these look different, but if you put them in your calculator, you're going to actually find out that these two are the same. And the reason they're the same is if I go back to before I simplified this function here, if I take 4 ln of 3 squared, one of our rules when dealing with logarithms is I can take the square, if there's an exponent inside my logarithm, I can actually move it to the front and multiply by my exponent. So this is equivalent to 8 natural log of 3, which is what I happen to get on the bottom. So even though these look different, they're going to give you the same value. So I can say that that's my limit, that my limit is 4 natural log of 9 or 8 natural log of 3. Either of those would be accepted as a correct answer. So remember, if there's less than or equal to's, you've got to check to the left and the right. If there's a not equals, then all you have to worry about is plugging it into the not equals part of the piecewise function. So careful on those ones. Number 11, find the values where this function is discontinuous and label these discontinuities as removable or non-removable. What is the vertical asymptote? Now, this is a lot more like something you might see on the AP test, because this wants to know, here's a function. Can you recognize what it means for a function to be discontinuous and what type of discontinuity that is? And then it would want you to label the vertical asymptote. So remember, the points of discontinuity are where our denominator is equal to 0. So what we're looking at to find what values of x make this function discontinuous is when I plug, what x's do I plug in so that I end up with 0 on the bottom? And a lot of you can just do that in your head. You can look at, well, what squared minus 4 is equal to 0? And if I do x squared equals 4 and take the square root of both sides, I end up with x could equal the positive 4, or it could equal the negative 4. Or sorry, positive 2, negative 2, the square root of 4. So there's actually 2 points at x equals 2 and x equals negative 2. One of the other ways to see this is if you start trying to remove that discontinuity. If you start trying to factor this, you end up with the x minus 2 on top. But the bottom is that difference of squares on the bottom. So that just becomes x plus 2 on the bottom and x minus 2 on the bottom. And this is what helps you recognize which one is the removable and which one is non-removable. Because this x minus 2, that x minus 2 is removable. We can actually remove that one. So we have to be careful, because when x minus 2, if x minus 2 is the one that I can remove, that's the one where x is equal to 2. Don't look at just what's inside the parenthesis. You can't say negative 2. When x is equal to 2, then I can that's the one that I can remove. So it's still a discontinuity, but it's my removable discontinuity. And I'm left with 1 over x plus 2, which means that when x is equal to negative 2, that's the one that I could not remove because it's still there. That one's my non-removable discontinuity, because when I plug in negative 2, I still have a 0 on the bottom. But if I were to plug in a 2, I'm not discontinuous anymore. So negative 2 would be your non-removable, 2 would be your removable. And then it asks you, what's the vertical asymptote? Well, your vertical asymptote is just your discontinuity there on the bottom. So your non-removable discontinuity would be where your asymptote is on the graph. So you would say that x equals negative 2 is your vertical asymptote. And if you need to see what this looks like, go ahead and graph it. If I say that y equals, again, if you don't need to see this, you're welcome to skip it. But if I say that x minus 2 is on top, and on the bottom I have x squared minus 4. When I graph that, I'm hoping that at negative 2, I see an asymptote. And I do. Right there at negative 2, I can see that I have an asymptote. And then as I approach 2, my other discontinuity, and here's where you need to be careful. Some people are going to miss this because all they're going to do is plug this in the calculator and look for asymptote or holes in the graph. Well, we know based on our algebra that there should be a hole right here at x equals 2. But because of the way the calculator graphs things, you don't actually see that asymptote, that removable point. So if I go to my table and I plug in the value of 2, I'm going to get an error at that point. Even though it looks like it's there, it's not actually there. And that's just a limitation of the calculator, and something you're going to have to be careful of working with your calculator on the AP test. And that's one of those important reasons why you understand what's happening in this problem and not relying solely on the calculator to do the work for you. Okay. All right, so number 12 asks us, at which values of x is f of x discontinuous? So this one isn't as interested in which one's removable, what's non-removable. It just wants to know what are the values that it's discontinuous. Again, you can be brave, put it in your calculator and hope that you can visually see it or that the table will show you those exact points. But I would rather trust my algebra. So what I'm going to do is try and simplify this in a way, try and get rid of something if possible. And I'm going to do that by factoring the bottom. So I know that I'm going to have x plus 5 left over on the top. And you know what? I'm going to actually get rid of all this other mess so I have a little bit more room to work with. I want x plus 5. That's got to stay on top. But this bottom piece, I want to factor. So I've got 2x squared plus 7x minus 15. And I'm going to go through this the way that you learned it in Math 2 Honors with McConnell, because that's probably where you learned how to do this. But he would have used the x method, x factoring. He would have put, but because of this 2 in front, I can still put my 7 on top, but I can't just put negative 15 on the bottom because I've got this 2 out front. So I actually have to put a negative 30 on the bottom. And I'm looking for what multiplies to negative 30 and adds up to 7. That's going to be a positive 10 and a negative 3. And if you're not careful, some of you are going to say, oh, well, that means that I've got x plus 10 and x minus 3, which isn't true because of this 2 out front. Remember that you have to divide both of these factors by your a factor, by whatever your a value is. So the 10 becomes 10 over 2, and the negative 3 becomes negative 3 over 2. So what you actually have is 10 over 2 reduces to 5. So I can put x plus 5 in one of these. My other one doesn't reduce. I get negative 3 over 2. And one more step that you haven't done in a while is I can't just say x minus 3 halves. Remember, when you divide by your a factor, what did McConnell call it? Bottoms up or something like that. You have to get rid of this fraction. Well, we want to. I mean, you could leave it like this, but you're not gonna get what you want when you multiply it through. So what I need to do is multiply everything by 2. You just move that 2 up in front of the x. So it becomes 2x minus 3. So now if you were to FOIL this, you would end up with the 2x squared plus 7x minus 15. If you didn't learn the x method, there's other ways that you can do that. If you need help with it, come see me. We can do some examples in class. Otherwise, there's my discontinuities. I know that when I plug in negative 5, this is going to become 0. So when x equals negative 5, I'm going to have a discontinuity. And then this side, when 2x minus 3 is equal to 0, I'm going to have a discontinuity. And my discontinuity, when I solve this for x, is going to be x equals 3 halves, because I'm going to add the 3, divide by the 2. So my other discontinuity is when x is equal to 3 halves. Now, I don't have to say which one's removable and non-removable. I could, because the x plus 5 cancels out. This is my removable. This one, because it's left, is my non-removable, which means that's where my asymptote's going to be if I were to graph this one. All right, let's move on. Number 13. Now we're getting a little bit closer to some of the more recent stuff that we've done. I know limits is going to be a heavy example on this test. We're going to get into derivatives here in a minute. Limits is definitely going to be the focus. So number 13, determine whether the statement is true or false. If it's false, give an example to show that it's false. So if the limit as x approaches 6 of f of x equals 36, that means that at f of 6, my answer is 36. So is that statement true or false? Well, hopefully you can say that it's false, because we don't care what happens at 6. F of 6 could be anything, as long as we're getting close to 36 as I'm getting close to 6. And as far as giving an example, you could explain that. You could use the law, the limits, the rules that you have there to explain why this doesn't necessarily have to happen, because it doesn't matter what happens at 6. It matters what happens near 6. You could also just give an example. You could give a graph of something that when you get to x equals 6, let's say that this is 36 up here. You could have just a horizontal graph, but when you get to f equals 6, you could drop down to 0. And you could give a visual example. You could also do something like a piecewise function. You could say, well, what if f of x was, what's going to be the easiest way to do this? Well, using this graph, let's say that f of x is equal to 0 when x is equal to 6. But at all other points, x is equal to, let's say, x squared. Oh, when x does not equal 6. So we're saying when x does not equal 6, then I plug in the function x squared. When x does equal 6, I have 0. So what this piecewise function would look like is just a parabola shifted. Well, I guess we're not shifted at all, right? We've just got x squared. But when I get to the point 6, when I plug in my 6, I'm going to have a hole in my parabola. All right. So you can give a visual example, you can use an explanation, or you can give me an actual function that shows that we get near 36 everywhere else as we approach 6, but at 6, we're not actually using that value. Number 14. So getting away from limits just a little bit, finally, right? If f of x is equal to negative x squared plus x, what's the derivative of f of x? So a lot of you noticed some patterns when you were doing the homework finding derivatives. And that's one of the reasons why we're not going to focus too much on it on this test, because we're going to start using some patterns that you may have recognized. But for this test, I do want you to use this limit to show me what the derivative is. If you know the shortcut, if you've recognized that, if you figured that out, great. Check your work that way. But I do want you to use the limit formula to show me what the derivative is. And remember, that's the one where you put the brackets and then the parentheses, and you replace the x with x plus h. So what I would do, first of all, if you've recognized the shortcut, you might be able to really quickly tell me that f prime of x is going to equal negative 2x plus 1, which again is accurate. That's true, but I want you to be able to show me using this limit formula. So the limit as h approaches 0, and then I want my brackets up here minus my parentheses all divided by h. So in my brackets, I'm going to put the function, but instead of x, I need to replace it with x plus h. So I get negative parenthesis x plus h squared plus parenthesis x plus h. So I replaced all of my x's with x plus h's. And then in the parentheses, I just use my original negative x squared plus x, my original function. Now, hopefully you've seen enough of these x plus h squareds to know that really just becomes negative x squared plus 2xh plus h squared. And then I have plus x plus h. So when I distribute this negative, and I've got the rest of this, but we'll follow that up after I distribute this negative. So I've got negative x squared minus 2xh minus h squared plus an x plus an h, and that takes care of my brackets. But then I also have my parentheses that I need to distribute this negative throughout. So I get a positive x squared minus x. And all of that's on top with h on the bottom. And remember, when you do this, everything from the parentheses that you distributed to should cancel out. So my x squared, if I did it correctly, should cancel out with a negative x squared. And my negative x should cancel out with this positive x. So what I'm left with is negative 2xh minus h squared plus h over h. Now, before I plug in, because I have a limit here, I'm looking at what happens as h approaches 0. Before I do that, everything on top has an h, and so that's going to let me cancel out my h on the bottom. So negative 2x is going to lose its h completely. The negative h squared is going to cancel out to negative h, and the h is going to cancel out to a plus 1. Please don't just get rid of the h, because h over h isn't 0, it's plus 1. So now, as h goes to 0, I can plug it in. Don't plug it into the x. I end up with negative 2x. This becomes 0 plus 1. And if I'm using my derivative notation, I would put f prime of x, which matches what we got if you recognized the shortcut, which some of you may have already noticed, and maybe you haven't seen it yet, which is fine, because we're going to learn about that in the next chapter. So moving on to 15. Well, we won't check that one today. We'll get to that another day. 15, f of t equals 2t squared plus t minus 3. And it wants me to find the average velocity, the instantaneous velocity, and the tangent line equation. So this goes clear back to the first homework. And remember, average velocity is just the slope of your secant between those 2 points. So that's just your y2 minus y1 over x2 minus x1. That's your average velocity. So if I go ahead and let's just do that. Let's plug these in. So when x is equal to negative 1, and I plug that into my function up here, I get negative 1 squared, which is 1, times 2 is 2. Minus 1 is 1 minus 3. That gives me my y is negative 2. Now when I plug in 2 squared is 4, times 2 is 8, plus 2 is 10, minus 3 is 7. So let's call these my x and y2, and let's call these my x and y1. So to find my average velocity, I just plug them into my slope formula. So we'll do y2, so negative 2 minus y1, over my x2, my negative 1, minus my x1. And that gives me negative 9 over negative 3, which tells me that my average velocity between those 2 points, on average, my slope is 3. Now my instantaneous velocity at x equals 0. Now when we learned this in the first section, we'd find what our x and y are when x is 0. So I would plug in the 0 and find that my y value at this point is 0 plus 0 minus 3. So my y value is negative 3. And then I would pick a point really close to 0 and plug that in and find a y value. So let's go ahead and do that. Let's say, well, what if x is 0.001? Is that the one that we want to use? I mean, either way, this is going to be an ugly answer because I'm plugging it into 2x squared plus x minus 3. So when I plug that in, and I'll let you do that on your calculator. Maybe we should do it. Again, you can fast forward if you want to. But if I plug in 0.001 for my x, I end up with 2 multiplied by 0.001 squared. And then I need to add 0.001. And then I need to minus 3. So when I do that, I end up with negative. My y value is going to be negative 2.998998. So negative 2.998998. And I'm not going to round yet. I'm going to go ahead and leave it right there because I want to get as close as I can to my actual x and y. So again, back to unit 1, we went and we found our x and y at 0 and then really near 0. And then we just plugged those values back into our slope formula. So let's call this one 1, and let's call this one 2. So my y2 minus y1 over x2 minus x1. This time, though, we're finding the slope of our tangent, or we're estimating it, I guess. So my y2 is negative 2.998998, and then I'm going to minus my negative 3 over my x2, which is 0.001, minus my x1, which is just 0. So that comes out to, I already have my negative 2.998 here, and the minus 3 becomes a plus 3. So on top, I end up with 0.001002. And on the bottom, I end up with 0.001. And when I divide those, so now I'm going to take this answer and divide that by 0.001, I get 1.002. Which looks like it's really close. It looks like I'm getting really close to 1. All right. Now, if you recognized the derivative shortcut, another way that you could have done this one is remember that the derivative gives me a formula that will give me my slope at any point. So if I were to look for f prime of t, if I'm looking for f prime of t, then again, those of you that recognized that shortcut, my 2t squared becomes 4t, and my plus t becomes plus 1, and my negative 3 disappears. So all I have to do is plug 0 in, and I get 0 plus 1, which equals 1, which is really close to what we found using it the old way, doing it the old way. So it's just two different ways to find the same answer. You also could have done it the limit way. You could have done the limit as x approaches 0 of f of x plus h minus f of x over h. But plugging x plus h into this function, it works if you don't recognize the shortcut. And you would have come up with the same answer. You would have ended up coming out with, once you plugged in 0, you would have come out with 1. Actually, you would have come out with 4x plus 1 as your limit function, as your f prime. And then when you plugged in 0, you would have come out with 1. Any of those ways work. If you recognize the shortcut, great, use it. If you like the limit formula, use it. If you want to just go back to using our tangent slope formula when we just got really, really close to 0, all of those methods are okay with me. Now we need to find the equation of the tangent line at x equals 0. And we know our slope at x equals 0. Our slope is 1, or if you used 1.002, I'm okay with that. So our formula says y minus y1 equals m times x minus x1, where x1 and y1 are just our point right here. So y minus 1 equals our slope, which is 1, multiplied by x minus 0. So I get y minus 1 equals 1x, which is just y minus 1 equals x, which is y is equal to x plus 1. Actually, no. Our y1 when x was 0, I'm looking at that going, that doesn't seem right. When x is 0, when we plugged that in up here, we found that our y value was negative 3. So this shouldn't be 1. This should be negative 3, which means this should be positive 3, which means this should be x minus 3. Getting ahead of myself. I'm plugging in the wrong numbers there. So we can check this, y equals x minus 3. Remember, I can go to my calculator. I can go to y equals. I wouldn't want to do this to find it, but I can definitely do it to check my answer. And I'm going to put 2x squared plus x minus 3. And remember that if you go to your graph, we can see what this function looks like. And if I want to know what my tangent my equation of a tangent line is I can go to second draw, and number 5 is my tangent line, and I just plug in my x value of 0, and it tells me what it'll show me my tangent line at that point, and it'll also give me the equation. So y equals 1x plus a negative 3. Y equals 1x plus a negative 3, which is the same thing as y equals x minus 3. Now, simplifying things on the AP test, this right here would have been an acceptable answer. This right here would have been acceptable. This right here would have been acceptable, and so would have our final answer down here, as long as you simplified correctly. But you could have left it in this notation up at the very beginning on the AP test. You don't have to, remember, if you don't have to simplify all the algebra on those final answers. Okay, last problem. Looking at the limits graph, just visually, looking at the graph. So as x approaches 1 from the left, I want to know what's happening as I approach 1 from this left-hand side. I don't care what's happening at 1. And these should be, those didn't print very good. These should be dashed lines because these are your asymptotes. That just didn't print out that way. So as x approaches 1 from the left, so I'm going to start from the left and I'm going to approach 1, and clearly I'm jumping up at that asymptote and I'm going up to infinity, which means that my limit does not exist. Okay? Now approaching 1 from the right, as I'm coming from the right, my y value all of a sudden is going to drop down because of that asymptote. So my limit, I'm approaching negative infinity, which again means that the limit does not exist. So from the left, I go to infinity. The right, I go to negative infinity. Either way, my limit does not exist. You could not say that it goes to infinity because they both don't go to infinity. So whether you're using doesn't exist or the infinity is as your answer on the last part, it has to be that the limit does not exist. Now, f of 1 just means what's my y value when I plug in 1 for my x. And at 1, I've got this asymptote, which means that there is no y value at f of 1. So it does not exist. Don't put that the limit does not exist. You can say that it's undefined at that point, but you can't say that the limit does not exist. It's not asking about the limit. It's just asking about this point. Now, looking as we approach, instead of our x going to a value, we're going to approach infinity. So as our x goes to negative infinity, as I go further and further here to the left, it looks like I'm approaching this asymptote down here, which is negative 2. And then as I go to the right, as I go to infinity, as my x goes to infinity, I'm approaching that same asymptote. So it looks like I'm approaching my y value of negative 2.